What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. In this video we're going to practice finding limits using important trig limits. So this is an example that we're going to go through in this video, and by important trig limits I mean these limits here, which are really important. If you're in a calculus course you need to know these, you need to have them memorized, and I actually made a video where I proved each of them, and that'll pop up in the top right here. In particular, the proof to this sine of x over x equals 1 is really cool. Hope you go check that out. But our basic strategy here is that we're going to plug in the number x is approaching. We always start with direct substitution. We're going to get 0 over 0, which is an indeterminate form, and we're going to apply a technique, which this technique involves doing some algebra and basically pulling out either sine of x over x or 1 minus cosine x over x, which is a limit that we know. And that allows us to find the limit of the entire expression. So let's start a little bit easy here. Here we have the limit as x approaches 0 of 3 times the sine of x over x. And again, we always start with direct substitution. So we're going to plug 0 in. The sine of 0 is 0. 3 times 0 is 0. So we have 0 over 0. So indeterminate form. And so this looks a lot like the sine of x over x. And we know that that limit as x approaches 0 is 1. The only thing messing me up here is that 3 out in front. But here's what I can do. I can actually take care of that 3. And it's actually kind of simple because if I rewrite it this way, it makes it a little more clear. This is 3 times the sine of x over x. 3 times the sine of x over x. So now what I can say is, well, we have a constant times a function, and the limit of a constant times a function, we have a limit law that says that's the same as the constant times the limit. So we can basically pull the constant out in front and multiply the constant by the limit of the sine of x over x, which we know is 1. And so this entire limit that we were given is just 3 times this limit, which is 1 because it's one of our important trig limits, and 3 times 1 is 3. Quick maths. Awesome. So we got our limit here, and let's step it up just a tiny bit. Very similar example. We have this inconvenient 3 that's making it to where we don't quite have sine of x over x, and this time the 3 is in a different place. In this first example, we had the 3 out in front. This time the 3 is in the argument, and this is really a key idea. I gave this example for a reason, which is that if we have the limit as x approaches something, I'm just going to leave it as a question mark, of the sine of something else, let's write it as, well, I guess we can just write it as x like we were given. As long as these two x's are equal and the number x is approaching makes them both 0, then this is equal to 1. Okay, so the argument needs to equal the denominator, and the number x is approaching needs to make each of them 0. And if both of those things are true, then the limit equals 1. So what we can do with this example, how this applies to this example, is that we really want this denominator to be 3x. If we were just given this, we could just immediately write 1 here. We weren't, we were just given x, but we can multiply it by 3 as long as we also do the same thing to the numerator. Okay, so I'm multiplying by 3 over 3. And what this gives me is that the limit as x approaches 0 of, and I'm going to write the 3 in the numerator out in front, just like I did in the last example, 3 times the sine of 3x over 3x, right? And now what I can do is the same thing, pull that 3 out in front. This is the same thing as the constant times the limit as x approaches 0 of the sine of 3x over 3x. Okay, so remember, argument has to be the same as the denominator. We got that. And the number x is approaching needs to make them both 0. And if both of those things are true, then that limit equals 1. And so we end up again with 3 times 1. Quick maths. That's just 3. So this is so cool because we put these 3's in 2 different places and we did 2 different strategies and we got the same answer for our limits. Kind of cool, these 2 examples. All right, let's jump in. Let's step it up a little bit, make it a little bit more difficult. This is the example we saw on the very first page. And now we're always going to start, again, direct substitution. I'm plugging in 0, and I'm getting the sine of 0 is 0, so 0 squared times 12, that's 0, minus 9 times the sine of 0, which is also 0. 0 minus 0 is 0 over 5 times 0. We have 0 over 0. But I'm just reinforcing checking because you could come across an example where direct substitution works and that just gives you the limit. But if you don't check and you try to do some algebraic manipulation, you may end up just spinning your wheels and wasting your time and not being able to figure anything out when you could have all along just plugged the number in. So it is important to check that. Okay, we get 0 over 0 indeterminate form. This doesn't directly look like sine of x over x or 1 minus cosine x over x. But I'm going to start with this. I'm going to just pull out a common factor from the numerator. I'm going to pull out the greatest common factor. Okay, so let me write a big fraction bar here. 12 and 9 have a 3 in common. And then we also have a sine of x in common. And when I pull that out, what are we left with? Well, 3 times what equals 12? That's 4. And we still have a sine of x there. Minus, let's see, 3 times 3 is 9. And that's just it, because we only had one sine of x, and we pulled that out in front. All right, so this is equal to the numerator of the original function, and I'm leaving the 5x down here in the bottom. And now here's what's cool, is I see a sine of x here, and I see an x here. So I'm actually going to split up this fraction into the product of two fractions. This is pretty cool. Check it out. I'm just going to go ahead and write it out. All right, here we go. I split up our fraction into the product of two fractions. If I multiply these together, I get exactly back where I was. They are exactly equal. And here's what's cool is I'm seeing a sine of x over x. And now I can apply another limit law, which tells us that the limit of a product is equal to the product of the limits. So I can basically split this up into two limits. One being the limit as x approaches 0 of this first piece here, which is 3 times, let me actually use a bracket, be consistent, 3 times the sine of x over 5 times x times the limit as x approaches 0 of, and this time I don't have to write it over 1. I did it to emphasize that I was splitting this up. I'm just going to write it like this. 4 times the sine of x minus 3. All right, this is cool. The limit of a product equals the product of the limits. And now I am so close to having sine of x over x. This 3 and this 5 are messing me up, but I can pull that out in front as a constant, 3 over 5. So here's my final step, is I'm pulling 3 over 5 out in the front here. And so I'm left with the limit as x approaches 0 of the sine of x over x, which I know is equal to 1, times the limit as x approaches 0 of 4 times the sine of x minus 3, which I don't know off the top of my head, but here's what's cool. Sine's continuous. I can plug 0 in, direct substitution, and find this limit pretty quickly. All right, so what do I have here? I have 3/5 times this limit, which is 1. That's one of our important limits. So 3/5 times 1 is just 3/5 times this limit. Let's do direct substitution. The sine of 0 is 0. 4 times 0 is 0. 0 minus 3 is negative 3. So times negative 3, which equals negative 9 over 5. Negative 9 over 5 is our limit. So again, our strategy, direct substitution, 0 over 0. Factor, recognize that I see a sine of x over x in there, and that's a limit I know. Pull that out, take out a constant, so I directly have that, replace that with what I know it is, and what I'm left with is actually continuous, and I'm able to actually evaluate the limit. All right, let's try another example. Limit as x approaches 0. We're going to plug 0 in, direct substitution. 1 plus 0 minus 1. The cosine of 0 is 1. So we get 0 in the numerator and 0 in the denominator, 10 times 0. So we're going to continue. I see a 1 and I see a minus cosine x. I'm just going to start by putting those next to each other. So I'm going to rewrite this as the limit as x approaches 0 of 1 minus cosine x plus 5x. That's a limit that I know. I know 1 minus cosine x over x. And so I'm just going to kind of put those together. And now here's what's cool about these different examples is here we broke up the function as the product of two expressions, right? Here we can't do that because the numerator, we can't like factor in a way where we can break it up as multiplication. Instead, we're going to have to break it up as addition. We can break this up as the sum of two expressions. Here's how we're going to do it. I'll go ahead and write it out. All right, so I've broken this function up as two expressions added together. Remember, when we add two fractions, we add across the numerator and keep the denominator the same. So if we add these two, we get right back to exactly what we have. These are exactly equal. And now here's what's cool is I'm going to be able to split it up using another limit law, which is that the limit of a sum is equal to the sum of the limits. So let me go ahead and break this up as the sum of two limits. All right, now this is really close to being 1 minus cosine x over x, which I know the limit of as x approaches 0 is 0, but I have this 10 down here in the denominator messing me up. So how am I going to take care of that? The same thing we've been doing. I'm going to pull it out in front as a constant. I'm not going to pull out 10, but I'm going to pull it out as 1 over 10 because the 10 is in the denominator here. So now what I have is that this equals 1 over 10 times the limit as x approaches 0 of this limit that I know, 1 minus cosine x over x, plus the limit as x approaches 0. And I think I'm actually going to go ahead and simplify this. I'm going to cancel those x's, which I can do. I can remove that discontinuity. It doesn't change the value of the limit. I'm just removing the whole, and now I'm finding the y value of the whole, which is the limit. All right, let's start back here in the beginning. 1 over 10 times this limit. Remember, this limit is 0. 1 over 10 times 0 is 0. So that first term is equal to 0, plus the limit as x approaches 0 of 5 over 10. Well, as x approaches 0 of a constant, it doesn't matter what number was down here, actually. It's just the constant 5 over 10, which we can simplify, reduce down to 1/2. 0 plus 1/2, quick maths, that's just 1/2. And so we've seen two different examples, one where we used sine of x over x and we split the function up as a multiplication, and one where we used 1 minus cosine x over x and we split the function up as addition. Pretty cool. These examples are so fun. We still got two more. I just thought these were kind of interesting. I don't know if they're as difficult. This one, I guess the difficult part is it's not clear whether we're going to use sine of x over x or 1 minus cosine x over x. But let's start with direct substitution. Tangent of 0 is 0 over 0. Boom. 0 over 0, indeterminate. Now here's what I'm going to do. I'm going to rewrite tangent as sine over cosine. Right? So that's going to give me something that looks a little more familiar. Each of our important trig limits, one involves sine, one involves cosine. So that seems like a thing that would be a smart thing to do. So here's what I'm going to do. Replace tangent with sine over cosine. This is our quotient identity. And now here's actually what I'm going to do. I'm going to rewrite divided by x as times 1 over x. I just don't like having fractions over fractions, right? I could write this over x and then I'll just deal with it now. I'll rewrite it as times its reciprocal, 1 over x. Now here's what's cool. I see a sine of x over x. Okay, so here's what I can do. I can actually rearrange this. I can swap these denominators. Why? Because when I multiply fractions, I just multiply across. Numerator times denominator. And multiplication is commutative. Cosine x times x is the same as x times cosine of x. So when we rewrite this, here's what's going to happen. We have the limit as x approaches 0 of the sine of x over x times 1 over the cosine of x. All right, so here's what we got. And now here's what's cool. I have another product. The limit of a product is equal to the product of the limits. So I can rewrite this as the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over cosine of x. All right, so I know that first limit. I know that first limit equals 1, so it's 1 times something. Do I know the second limit? Well, if I plug in 0, what happens? Direct substitution. The cosine is 0. Oh, I know that's 1. 1 over 1 is 1, so we have 1 for the second limit here. 1 times 1 is 1, quick maths, and that's this limit. So this is cool. I wouldn't call this an important trig limit. It doesn't come up really that much, but it's cool. Now if you ever see the limit as x approaches 0 of tangent x over x, you can say that equals 1. So sine of x over x and tangent x over x are both equal to 1. Awesome. We got one last example here. I just think this is a cool one. Secant. All right, first let's plug in 0. What is the secant of 0? Well, the cosine of 0 is 1, and secant is its reciprocal. So I know that if the cosine is 1, then the secant is the reciprocal of 1, which is just 1. 1 minus 1 is 0 over 0. So we do have this indeterminate form. I had to think about what the secant of 0 was for a second. We got this indeterminate form, and here's what I'm thinking we do. Secant and cosine are reciprocals, so I'm going to rewrite secant as 1 over cosine. Let's go ahead and do it. The limit as x approaches 0. And again, that's kind of our strategy when we see stuff like tangent, secant, cotangent, cosecant. We're rewriting in terms of sine and cosine because the important trig limits that we know have to do with sine and cosine. So that seems like a good strategy. All right, so here's what I can do. I can say the limit as x approaches 0 of 1 over cosine of x minus 1, and I'm going to do the same thing here. Let me add a parentheses here because the entire numerator is being divided by x, which is the same thing as multiplied by 1 over x. All right, this is how I choose to write it. You could write that all over x, that's fine. I like to do it this way. All right, what am I going to do here? Am I going to find a common denominator and combine these? I think that's what I'm going to try to do algebraically. The limit as x approaches 0. So here I can rewrite 1 as cosine of x over cosine of x, right? And so that's going to give me a common denominator, and I think this is going to work out pretty nicely because what I have here is 1 over the cosine of x minus the cosine of x over the cosine of x. And why I said this is going to work out pretty nicely is I noticed that this was going to combine to be 1 minus cosine of x in the numerator, which relates to the limit I know. All right, so I can subtract two fractions. They have common denominators now. I can just subtract across 1 minus cosine x. Let's go and rewrite that. This is equal to the limit as x approaches 0 of, in the numerator we have 1 minus cosine x. In the denominator we have cosine of x. And this is still times 1 over x. And now I'm going to do a similar swappity swap that I did in the last example where I said, oh, cosine of x times x. When we're multiplying two fractions together, right, we just multiply across numerators, across denominators. Multiplication is commutative, so I can swap these positions, and then I'm going to have the limit that I know the value of. So this equals the limit as x approaches 0 of, let me rewrite it here, 1 minus cosine x over x times 1 over the cosine of x. So I just swapped the x and the cosine of x. And now we're going to split this up. I'm kind of running out of room here. The limit of a product equals the product of the limits. So I'm splitting this up. The limit as x approaches 0 of, see if I have room, 1 minus cosine x over x, which we know is 0, times the limit as x approaches 0 of 1 over cosine of x. And now we're about to be done here. All right, what do we have here? That first limit, we know that's 0, times, what is the second limit? We can substitute. Cosine of 0 is 1. 1 over 1 is 1. 0 times 1, which just gives us 0. So the secant of x minus 1 over x, that limit as x approaches 0 is 0. Hopefully you learned something in this video. I had fun making it. This is fun stuff. Leave comments if you have any questions. Like the video, subscribe, do all that stuff to support me. But most importantly, keep flexing those brain muscles. I'll see you on the next one.